Today, we're looking at damped harmonic oscillators. This picture here has nothing to do with it. We were just talking, Trace and I, about phase diagram for something like carbon dioxide, something that's not water. A harmonic oscillator, we've learned, is something that follows the relationship. The net force is equal to minus kx, where x is the amount that it's been displaced from equilibrium. The minus sign is giving you the directionality that it's a restoring force, restoring it toward the equilibrium position. A damped harmonic oscillator is adding something that is going to take away energy. And we're going to look at a specific type of damping, a damping that's proportional to the velocity. If it's damped differently, of course, you're going to have different results. So let's start by looking at an undamped harmonic oscillator. And then once we've gone through this, we'll then go and look at it again using the damped harmonic oscillator. Now, this is going to require us to use differential equations. So when did you take differential equations? Yeah, you have. So what we're going to do is get to the differential equation. It's a second order linear differential equation. And then we're going to say, if you had taken differential equations, you would know how to find the solution and know that it's this form. And once we have that form, then we will go back and we will use that form solution. So we start with this diagram, and we are going to apply Newton's second law. So if we're going to apply Newton's second law, we need to identify all of the forces. We are going to not consider this one right now because we're considering it undamped, so we're just taking out the damping. Now this shows one force. That is not all the forces. What else do you have on this besides the force of the spring acting on our bob, our object at the end of the spring? Gravity. So we need to add on to this force of gravity. Now notice this problem has x defined as positive downward. So we have to pay attention to our directions as we do this. So staying with that, the sum of the forces in my x direction equals, and looking at this picture, what do I get by applying Newton's second law? Now, the picture leads you with a little bit of confusion because it has the arrow pointing up and says minus kx. Well, the magnitude of the force is kx, and the direction up is what gives us the negative sign. So because this is shown with it stretched downwards, that's going to be a positive x. So there we have it. Now, of course, according to Newton's second law, what is the sum of the forces equal to? It's equal to mass times acceleration. Now, instead of acceleration, I'm going to put the differential d second x dt squared. So I have a differential equation. We will usually take this equation and rearrange it so everything that has an x is on one side and things without x's are on the other side. And so I'll rearrange this to have md second x dt squared plus kx equals mg. And then we usually do one final step. We get the highest derivative so it doesn't have a coefficient. So I'll divide everything by m to get rid of that coefficient. And so I have d second x dt squared plus k over mx equals g. That's my second order linear differential equation. Now, you guys haven't taken differential equations. I'm not expecting you to, but I'm going to give you just some verbiage to help you when you get there. When it says second order, the order is talking about what's the largest derivative you have. And so the largest derivative here is the second derivative, hence it's the second order. And then I had linear. Well, we understand linear means straight line. We're good with that, right? But how's that going to apply to this? Right? This isn't y equals mx plus b. What it means in linear is if each term has x raised to the 0 or 1. 0 means it's a constant. 1 is linear. So I have the derivative, the second derivative there. That second derivative is raised to the power of 1. So that's linear in terms of x. And then the second term, k over mx, that's linear in terms of x. And then it's equal to a constant. So that's what makes it linear. So this is a second order linear equation. And so I've shown the work, right? It's the same equation, fortunately, right? I didn't make a mistake. How do you solve that beast? If it was a first order linear differential equation, I have shown you how to do that. The first order linear differential equation, actually I didn't require linear when I showed you. We separated variables and we integrated both sides independently. The second order, well, you can't quite do it that way. It takes a little more work. You'll learn that when you take differential equations, if you do. I know Alex is going to. Have you taken DiffEq? I will. You will, okay. You probably won't, right? You won't either. Maybe. Okay. Well, from differential equations, we know that this has a solution. It actually has two solutions. We have one solution that we call the particular solution. What does it mean to be the particular solution? The particular solution is the solution that gives you the answer. And then you're like, well, I thought that would just be called the solution. There is also the homogeneous solution. The homogeneous solution is the solution that gives you 0 instead of the answer. You know, if I have an equation and I can have a solution for the left-hand side that's equal to 0 and a solution for the left-hand side that's equal to, in this case, g, then my total solution could be just the sum of the two. Because one gives me g and the other gives me 0, it's still equal to g if my solution is the sum of the two. That's what the deal is with the particular solution and the homogeneous solution. The particular solution is what gives me the answer on the right-hand side. The homogeneous just gives me 0, so it's something I can add to my solution and it doesn't change anything. So we have to have two different calculations for the solution. The particular one is the easier one here, so I did it first. So for the particular solution, I have to have it equal to g. Well, if x is a variable, if it's changing value, the only way I can have an x changing value, but it's equal to a constant, would be if the second derivative just gave us a constant plus the original, right? Well, the second derivative given us the original is the homogeneous solution. So the particular solution is only going to be if my x is constant. So my particular solution, xp is equal, well, notice it's k over mxp is equal to g. Solve that for xp. And xp is equal to gm over k. So this is the particular solution. So my end result is going to be whatever I find for the homogeneous plus this offset. Can you tell me the physical meaning of this offset? That's the equilibrium position.
That's the homogeneous solution, right?
No, that's the particular solution.
Why is it just G?
It's not just g because we're saying the only way that this can be true is if x is constant. And if x is constant, then the second derivative of x is going to be 0 because derivative constant is 0. So we have 0 plus k over m xp equal to G. And then we just multiply by M divided by K. So that's our particular solution. Now we go to the homogeneous solution. There's the same differential equation, but now it's equal to 0.
So it's like basically, like it looks like that, only you like separated your variables.
I didn't follow that.
I don't know.
Okay. This here, in differential equation class, you learn that the solution has this form. Where C is some constant. And so what we do in this class, since we're not in differential equations, we're not expected to be able to find that X homogeneous has this form. But what we can do is we can say, oh, if X homogeneous has this form, then I can put it into my equation and find what value C has to have to satisfy the homogeneous equation. So my equation has the second derivative of X. So I have to take the second derivative of this. So what is the second derivative of e to the CT? Let's start with the first derivative. I shouldn't go straight to the second derivative. So if X sub H is equal to e to the CT, then d X sub H dt is equal to, what's a shorter way of writing that? X sub H with a dot over it. Dot means with respect to time. The apostrophe means with respect to position in physics. Okay, so if I take that first derivative, what do you do when you're taking the derivative of an exponential?
It's the same thing, but you bring down the exponent.
Okay, same thing, but you bring down the derivative of the exponent. So my exponent is CT. What's the derivative of CT? C. Or if you prefer, that's equal to Cx sub h. Well, given that the derivative of x sub h is just a constant times x sub h, then x double dot of h, the second derivative, what's it going to be? C squared e to the CT, or C squared x sub h. So now I'm going to take this and put this and this in their appropriate places. And so my differential equation becomes C squared, I'm going to change color, sorry about that. C squared x sub h plus x sub h equals 0. Right? This one was C squared x sub h. So that's, oh, I forgot the K over M. Forgot the K over M. Glad I went back there. Now, the next step is not tricky, but there is a common mistake people make. The common mistake people make is they say, oh, I have x sub h in both of them, so I'm going to divide it out. Can anybody tell me why that would be a mistake? Well, all we're looking for is what condition makes this equal to 0. But x sub h could be 0. And if you divide by 0, you've made a mathematical error. So the correct way to solve this is to factor out x sub h. And now we have two situations that will make this equation true. What's the first situation that will make this true? That is a solution. It's always a solution. Is it useful to us? When we talk about its vibration, we say it's not moving. Is that a useful vibration? Ashley said no. She's correct. So we call this the trivial solution. When I was taking DiffEq, we loved the trivial solution. If the teacher didn't say something about not using the trivial solution, we would write it down because it saves you a lot of time. I found a solution. It's the trivial one. That's not the one we're looking for. It's like those droids. So instead, we look at the other one. C squared plus K over M equals 0. If that's 0, the whole thing is 0. Well, K and M were physical parameters. K is a physical parameter telling us about the spring. M is a physical parameter telling us how much mass we have at the end of the spring. C is the only thing we can solve for here. So this requires that C is equal to, and I'm going to write this with an equation or with an error. There are actually two errors here. Okay? There's a negative there. What's the other error? Shouldn't it be what? No, there's no X in here. Needs to have a plus or minus. Whenever you do the square root, you have two answers, a positive answer and a negative answer. Well, now, in case people are confused about the minus there, the first step, I didn't write the first step. The first step was C squared equals minus K over M. Then you do the square root, so that minus sign is inside the square root. How do you deal with a minus sign inside a square root? It's I. Now I have to share with you guys, read Calvin and Hobbes. There's one comic strip where Calvin is supposed to be learning about imaginary numbers, and he asks Hobbes, what's an imaginary number? And Hobbes says, oh, that's easy. That's numbers like 12-teen and no. Imaginary number has a very specific meaning to us in math and physics. The square root of -1 is the imaginary number. And it's useful. It's not just wasted time. And you can take a complex analysis course to learn how it's useful. Or you can take complex variables, which it turns out, Alex, is apparently not taught next semester. And it's also not complex analysis, it's just complex variables. So it's taught at a much lower level than we were anticipating. Just because we were talking about that. So this is equal to plus or minus I square root K over M. Now, in the other physics class, we've seen the square root K over M. What did we call that? We called that our resonant frequency. I'm going to write omega sub 0 for our resonant frequency is equal to square root K over M. So this will be a definition. Put a third line in equal to make a definition. So C is equal to plus or minus I omega 0. Now you look at that and you probably aren't feeling all that satisfied. What have I found? I have found the value of C. How many values of C have I found? 2 imaginary ones. And so oftentimes, somebody who hasn't done this in the past, which is all of you, feels a little disheartened, like, I don't feel like I've really done anything useful. Well, let's come back in. We have 2 solutions, so our actual homogeneous solution is just a linear combination of the 2. It's going to be some constant that is determined by how you started the physical vibration times the first solution, so e to the, I put C plus for the plus sign, t, plus another arbitrary constant. I use A and B for my two constants. That's set, I say it's arbitrary, but it's set by how you start the vibration. E to the C minus T, where C minus is using the minus sign. So putting in the solution we just found, this is equal to A e to the I omega 0 T plus B e to the minus I omega 0 T. So there we have our solution. And we all say, huzzah, we have a solution. What does it look like? How can I graph this? How can I graph my display? Is the displacement an imaginary number? It shouldn't be. That's a very physical thing. Physical things can't be imaginary. Math can be imaginary. Physical things have to be real. You have to remember that for quantum mechanics.
That's going to come up.
Yeah.
Like as an issue, like they're going to discuss it.
Well, as a reminder, if you find an answer that says that your momentum is imaginary,
Oh,
you made a mistake.
okay, good. I thought it was going to be something like debated.
No. Sure, we have imaginary momenta. When we talk about things like, the isospin. Okay, we'll try not to talk about that ever. Okay. So how do we plot this as a real function? When you get to electronics, you'll see that we use this as well, and we say that there's an imaginary part and it's not real, and so we don't plot it. That feels good. Well, we are going to use Eulers equation. Now, do I have Euler's equation here? Yeah. Well, this is just going down what we've just done. Yeah, here's Euler's formula. Euler's formula, and yes, that is how you pronounce this, is Euler. Because all of us being Americans, we'd say something like Euler. Euler's formula is that E to the I theta can be broken up into a real part and an imaginary part. The real part is cosine theta. The imaginary part is I sine theta. So if we take our expression there, xh is equal to a, e to, and so on, we could rewrite this as, and now I wrote this, I did some extra work in between. If we want to be technical here, we'd have xh is equal to a times cosine of omega 0 t plus I sine of omega 0 t plus b cosine of omega 0 t, put a minus sign there, plus I sine that would be the correct, I forgot the minus sign. I erased it so I can make the minus sign more obvious and forgot to write it. It's fixed. That would be the direct substitution. And then we have to use a little bit of our brilliance. Cosine is a symmetric function. That is, cosine of plus theta and cosine of minus theta are exactly the same. So I can just go ahead and erase that minus sign, and it made no difference, which is why I originally wrote it without the minus sign, because I went too fast. Sine is an anti-symmetric function. Sine of minus theta is equal to negative sine of plus theta. So for the sine, it's a little more complicated. I go like that, and I change both signs, both the one that was inside and the one that was outside. And I got to remember final parenthesis. So that is X homogeneous using Euler's formula. But now we can see, hey, look, this is simplifiable. That's equal to a plus b cosine of omega 0 t plus a minus b I sine of omega 0 t. And most every one of you is probably saying, I still see a problem. What's the problem you still see? There's an I. There can't be an I. I told you that. Well, who said that A and B were real numbers? I never said that.
You never said they weren't.
I never said they weren't either. I just said they're arbitrary constants based on our initial conditions. So they're no longer arbitrary when you have initial conditions. So A and B can be complex. That is, A could be actually, that's going to be the wrong sign. Let's just say A is C over 2 minus I D over 2.
Yeah, that's the most reasonable thing for him, right?
It certainly is. And for B, here's something else that's reasonable. C over 2 plus ID over 2. Perfectly reasonable. Okay, why did I do this? I did this because we just say A plus B has to be real, which means that the imaginary parts of A and B have to be the same magnitude but opposite signs. And then we have A minus B has to be imaginary, which means that the real parts have to be the same. And so that selection made them so I would have a real XH. And then we can go through and you see A plus B is C. And A minus B is minus ID. But minus ID times I, what's I times I? Minus 1. So minus ID times I is just D. And so using these definitions, that's the same as C cosine of omega 0 t plus D sine of omega 0 t. Now we have something that fits our understanding. It's all real. And it's a sinusoidal function. My son Nathan is taking trigonometry right now. And he has learned in trigonometry that you can take this and you can also write it as another constant. F is square root of c squared plus d squared times cosine of omega 0 t plus a phase angle. So that phi is just the phase angle. It tells you that instead of, if you have a cosine curve, its maximum occurs at time equals 0. If you have a sine, its maximum occurs at time is equal to 1/4 of the period. And that phi is just going to make it so you can shift it anywhere, because when you're doing sine plus cosine, depending on the values of C and D, it can shift where the maximum occurs. So this is an equivalent form. In fact, all three of these are equivalent to the same thing. So what this gives us is a sinusoidal function, something that's just going up and down at a constant frequency, angular frequency omega 0. So here we've gone through all the calculus to solve the simple harmonic oscillator. Was that the goal? No. That was the starting point. The goal is to look at the damped harmonic oscillator. So we add in the damping force. Damping force is a force that's in the opposite direction from the velocity, so that your force is doing negative work, taking away energy. And we're choosing a linear damping force. Why? Well, if we have something that's going through a fluid at a relatively slow speed, then it's going to be a damping force that is linear with speed. So this is real. This is what you typically have at low speeds. And so now we redraw the picture, and this time I say redraw, of course it's exactly the same picture. This time I just don't black out one of the forces. So we have the damping force, we have the force due to friction, and we still have the one that Gila reminded us about. Force gravity is equal to mg. Notice I still start the same way, using Newton's second law. Sum of the forces in the x direction. And remember, our picture shows the x direction is down, so down is positive. What do I get applying Newton's second law now that I've added an additional force? Why I use C is because I didn't make this figure. We always use B. In fact, there's kind of a problem for my last solution where I used C as the exponent, because now I have two C's. Notice there I put B. So I'm going to put B because that's what we standard use. So I'm just going to change this from a C to a B to match the equation I showed. And since we have Newton's second law, what's that equal to? MA or M, save ourselves some time, mx double dot. Second derivative, well, V is x single dot. V is dx dt. So now I have an x double dot, an x single dot, and an x. It's still a second order linear differential equation. I'll rearrange it like I did before. Divide everything by m and put them all on the same side that have x's. So there's my second order, once again linear, because each of these x terms is raised to the first power. How many solutions am I going to have for this? You can think of this question multiple ways and still get the same answer. Two. One way you can think about it is, well, I'm going to have a homogeneous and I'm going to have a particular. The other way you can think about it is, for that homogeneous solution, because it's a second order differential equation, I have to have two solutions. So two ways to have come up with the answer 2. So we're going to have a homogeneous and a particular. For the particular solution, once again, it's going to have to be, okay, this is just writing what we did. The particular solution will have to be exactly the same as the undamped case, because your particular solution, because the right side is a constant, is going to require that x is a constant, which means the first and second derivatives are 0, and you just have x particular is equal to g mg over k. So that still has to be the particular solution. The homogeneous solution, it's a little more interesting, because now we have both the first derivative and the second derivative there. Well, last time through, we calculated what the first derivative is. We calculated what the second derivative is. So I'm just going to put those in. So I'm going to rewrite this equation, putting in my derivatives. So this is going to be, well, the first one is going to have c squared x homogeneous, right? Because that's what the second derivative is, plus b over m times cx. Cx did not come out. All right. Now what do I do? Cry. We cry a lot, okay? Well, what did you say, Gila?
Could we do Quadrant.
We will. We will first factor out the XH. And then we say, this gives me two solutions. I wonder if he'll let me get away with the first one. What does X have to be to make this true? 0. Well, that's our trivial solution. And so, no, I'm not going to let you get away with that. And so we take the second one and we solve for C exactly like Gila said. So for the second one, we're going to have C is equal to negative B over M plus or minus the square root of B over M squared minus 4 times 1 times K over M all over 2. And now you look at this, and I assume you don't cry. I'm going to rearrange this just a little by putting the 2 in the numerator. So I'm going to have C equals minus parenthesis B over 2M plus or minus square root of B over 2M quantity squared minus K over M. Well, how many values do I have for C here? 2. One with the plus sign, one with the minus sign. I'm going to define a new variable, or a new constant, excuse me. Let's define alpha is equal to B over 2M. It's called the Neper frequency or the attenuation. And I'll show you why it's called the attenuation in just a moment. And I have these words on the next slide. So if I use that, this becomes equals minus alpha plus or minus the square root of alpha squared minus omega 0 squared. Oh yes, K over M, omega 0 was square root of K over M, so K over M is omega 0 squared. Fortunately or unfortunately, there are 3 different regimes we can find relating alpha and omega 0. One regime is, what if alpha is greater than omega 0? Then the thing inside the square root has a positive side. And so I just have a real plus or minus a real. What if alpha is less than omega 0? Then the thing inside the square root has a negative sign, which means I have alpha plus or minus an imaginary number. And then the third case, what if alpha equals omega 0? Then I only have one root. But I said it's a second order linear differential equation. The second order requires 2 solutions. There's going to be a special solution if alpha equals omega 0. Once again, linear equations, you learn that stuff. So now let's look at our 3 solutions. So we've gotten to this equation. Did I forget a minus sign? Nope, I got it there. Okay. So the first case, the one we call underdamped. Underdamped means that the amount of energy we're reducing is a small amount. And if it's a small amount that you're reducing, then the Neper frequency is small, right? Since the Neper frequency is B over 2M, if B is small, then alpha is small. And so that's the one where you have the imaginary solution. And so we define, now if you look at this, you might note, what? Here I have square root of alpha squared minus omega 0 squared. And here I defined omega r as square root of omega 0 squared minus alpha squared. Why did I reverse the order? Because I want to factor out the minus sign. So I have imaginary, so that I have this second term is going to be I times omega r. So this omega r is going to be a real value. And so my solution C is alpha plus or minus I omega r, which means that my x for underdamped is, again, arbitrary constant A, e to the, and I have to put in the whole shooting match, so minus alpha plus I omega r t, plus B, put in again the whole shooting match, but with the minus sign. And combining those two, and I'm not going to go through the combining again and showing Euler's formula. Combine those, and we have both terms had this e to the minus alpha t term, so I could factor it out, and then f cosine of omega rt plus phi. So what do we see is, first of all, that's not omega 0. So this resonant frequency is not the same as the natural frequency we had if it was undamped. Is it bigger or smaller? You have omega resonance equals square root of omega natural squared minus alpha squared.
If you're damping to speed in general, you'd be like slowing it down.
You're slowing it down.
So the wavelength would be longer.
Okay, the frequency is lower.
Yeah.
Right, you can just look at that equation. Omega naught squared minus alpha squared, square root is going to be less than omega naught squared. So we have a lower frequency. By having the damping, we lower the frequency that it oscillates just a little bit. Depending on how much damping, you lower it more and more. The more damping you have, the lower the frequency is going to go. This term here, we would call the alpha, I said, was called the attenuation. The e to the minus alpha t has the attenuation effect. Attenuation means it's getting smaller. And so the amplitude is f e to the minus alpha t, right? Because cosine goes between 1 and minus 1. So whenever I multiply cosine by, it's going to be the amplitude, since cosine goes plus or minus 1. So e to the minus alpha t, as time gets bigger, e to the minus alpha t is approaching 0, so the amplitude is dropping in time. And that alpha is telling us how quickly the amplitude is dropping. And so the alpha, the Neper frequency of the attenuation, has a very real outcome. The bigger alpha is, the faster it's going to attenuate. So if we draw the actual motion, the first thing you do is you graph plus and minus your constant f e to the minus alpha t. So this is shown here with the blue dashed lines. That is our amplitude. Our oscillations are going to come up and hit the blue dashes each cycle. And then inside of that, you have to determine what the phase angle is for what phase you're starting with your cosine curve. And then you just draw the sinusoid with the starting phase correct inside of it. And that gives you a solution. So you're going to have oscillations that diminish with time. I talked about the car as an example of an underdamped system, the shock absorber. You push down, it should bounce up and down and come to a stop. It's coming to a stop because it's being attenuated by the shock absorber, the damper. It's oscillating because your car is built with the tires on springs. And so that's why it oscillates. So our car's suspension system is acting like an underdamped simple harmonic oscillator. Now, if you've got a plush luxury car, Anyone ever like push down on the bumper or the fender of a plush luxury car? It just goes. Psh. That's not very underdamped, right? It doesn't come up and oscillate. The idea is to give you a really smooth ride, but it's not what we would consider optimal for most conditions, but it's optimal for feeling smooth. So that's underdamped. Now we go to overdamped. Overdamped is when you have a very strong damping force, something that makes it so it can't even get to zero. It just goes. And so in that case, we defined beta now as alpha squared minus omega naught squared. What's the difference in beta and omega r? Okay, the difference is flipping the order of the alpha and the omega naught. We don't call it omega r because it's not going to resonate at that frequency, because that's real. Our solution is now C is equal to minus alpha plus or minus beta. You put that into your solution, and you have, I forgot to put, no, I didn't. It's all good. You have an attenuation term out front, and then what does e to the beta t do? As time increases, what does that term do? That term goes like this. The negative one is going to go like this. So the fundamental behavior is going to look mostly like these two together, because this one is going to zero and this, okay. This is going to zero, the attenuation, and this is also going to zero with time. So this term here very quickly is going to disappear because it's going to zero, the front one's going to zero, going towards zero. And so the fundamental shape, so if you look at the shape of the green, blue, and red curves, after you get past about where they all cross, that shape is basically just showing you a e to the minus alpha t, e to the beta t. The stuff before where they cross has some influence by the b term. So that's what overdamp looks like. The more overdamped it is, this green one is very highly overdamped, the longer it's going to take to get to zero. So overdamped is going to take a while to get to zero. Then we have critically damped. Critically damped is what occurs when alpha equals omega 0. When you would have for your solution of what we did, just minus alpha, plus or minus 0. Well, it does, but it doesn't oscillate. It didn't oscillate in overdamped either, right? In differential equations, you learned that then you just have a polynomial to make up the second solution. So we have a plus bt multiplied by that attenuation term. So the attenuation term is still there. And then we have a plus bt. Now this will give you a possibility of just one crossing of 0. So underdamped could go like this, or if it started like this, it could go like this. It's not going to cross 0 twice, but because of the function there, it can cross 0 once. Now, or I said underdamped, critical damped I meant. Critical damped can cross 0 once, can't cross it twice. When you're designing a system like the door closing thing here, you want to be pretty close to critical damping. But you actually don't want exactly critical damping, because it'll get to 0 fastest if it's slightly underdamped. If it's underdamped, it will cross 0 and oscillate with, around 0. If you're just slightly underdamped, it would have small oscillations about 0. Well, the door, of course, when it finally gets shut, it stops there. You want to come fast enough that it can get past the mechanism and shut. and then it latches and stays there. So something like this door stopper is designed to be slightly underdamped. So these things have real value. Now, we don't have time to go into any other real values, but buildings these days are built so that when an earthquake hits them, they'll vibrate with it. They don't make them rigid, because if you make it rigid, they'll break. So they're built so they'll vibrate with them, and then they have to put in things to dampen out the energy, because you don't want it to just keep vibrating. So what they've been doing at Loma Linda, they're building a new hospital there, is they built the foundation, and it's basically on wheels. So if an earthquake comes, the ground will move underneath the hospital, and it won't move as much. And then you have dampeners so that as the hospital does move, it'll move and it'll oscillate, and then you'll dampen out that energy and stop it again. I always wonder about things like, you have the utilities connected. I guess you put in hoses or something, right? Because if you have a rigid utility line, the gas line's rigid, and we allow the hospital to slide away, that could be catastrophic.